So in this part of our lesson, we will look at exponential functions used to model a data set. We'll do this guided example for problem 1, where we find a regression equation, and then in problem 2, we use the regression equation to answer a few questions. So we'll go through 1 and 2 here. In the year 2020, the world suffered a global pandemic, the outbreak of COVID-19. COVID-19 is spread through air droplets from an infected person. Many countries experienced 1 or more lockdowns in the early part of the year 2020 to reduce the spread of the disease. Below is the data of the number of new cases in Ghana in West Africa during a period of the global pandemic. James wants to analyze this data and use it to predict the number of new cases that might occur later at a later time in the year. The table below shows the data for the number of COVID-19 cases. Let T represent the number of years or number of months, since January. Therefore, January represents T equals 0. All right. So this is giving us information for the months of March through August of 2020. If January is month 0, then February is month 1, March is 2, April is 3, May is 4, June is 5, July is 6, August is 7, based on January being 0. Okay, then from here, we're asked to come up with an exponential regression function. We're going to round 3 decimal places. This has to be done in our graphing calculators. We're going to take the information from the table, make the inputs L1, the outputs L2, and then we're going to come up with our scatter plot and then find an exponential equation, not linear like we did before, an exponential equation that models this information. All right, so let's go to our graphing calculator. Okay. So once we get to our graphing calculators to do regression, we always go to stat, and we have to edit the statistics to put in the numbers that we have in our table. Now, I did this one earlier, so they're already here, but if you have something else that's typed in here, let's say this information was wrong, I just go to the 2, press delete, declare out all of those previous numbers, and then enter in the correct information. This was correct, so we'll leave it. Once we have this information in, now the calculator knows what data we're trying to plot. Then go to stat plot, so that second y equals, make sure your stat plots are turned on. Mine are on, so there's nothing for me to do. If yours are off, click on it, turn it on. And then from here, we want to plot the information that we have under statistics. We also want to clear out anything that we don't need, these old things. Let's clear those out. Okay, now let's go to Zoom and Zoom Stat, Zoom 9. And ta-da, this is a scatter plot of the points that we were given in the table. All right, so far, nothing that we're doing is any different than what we did before. And for the most part, like I said, the steps aren't going to be different. When we look at the scatter plot, you should notice that these points, at first they start off kind of low, and then it starts to increase very quickly. And then this one doesn't increase as quickly. But the first 5 points start off relatively small, then increase quicker and quicker. Because we can see that there's a small change at first and then a bigger change later, an exponential model would be good here rather than a linear model. Okay, so next we're going to find our regression equation. Remember, to do this, we go back to stat. This time we go over to calculate, and we're going to calculate. Oh, give me 1 second. All right, we're going to calculate the exponential regression. So this is the one step that's different. Before we would go to 4, that's a linear regression though. That's not what we want. We're gonna go down to 0, which is an exponential regression, EXP. So when we click this, we'll tell the calculator where our inputs are, where our outputs are, and then the calculator will give us an exponential equation that models this data. All right, so We hit enter here, and then L1 is where our X values are. L2 is where our Y values are. Go down to calculate, boom. And we're given our A value and our B value. So this is our equation. From here, we want to write out the, well, this is not our equation. This is our A and our B. We want to write out what the equation would be. So this is Y equals, we're asked around 3 decimal places, so we'll do that. Y equals 17.735 times 3.111 to the X power. That's what the exponential model looks like. Last thing we're going to do in a graphing calculator before we jump back into our workbook is check what this graph looks like with the scatter plot. So we'll go to Y equals, we're going to put in 17.735 times 3.111 to the X power. And graph this along with the scatter plot. So it kind of closely fits to those data points up until the last month. All of those points are kind of close to here. So it's an okay model. All right, then let's go back to our workbook and write down this equation that we got and use it for the next problem. All right, so for problem number 1, the equation that we found, we do need to be careful and make sure that we're using the variables that are given to us. So our input variable is t and our output is n of t. So we should write this as n of t equals 17.735 times 3.111 to the t power. All right. That's our equation. Now we're going to use this equation in problem number 2. So continuing from problem 1, write the exponential regression function rounded to 3 decimal places. Again, that was n of t equals 17.735 times 3.111 to the t power. Then we're asked, what is the practical domain of this function? So practical domain is what numbers make sense for the input. The numbers that we were given for the inputs in the table were 2 to 7. So you can say that's the practical domain. If you wanted to stretch out that domain a little bit, you could. I would say, let's say, T is anything from 0 to 12. That would represent the first 12 months. Well, that represents all of 2020 here, which is when we're given information. So it doesn't have to be exactly this. If you wrote something, there's a little wiggle room with your practical domains. If you wrote 2 to 7, I would take that. Or if you wrote 0 to 10 or something reasonable, a reasonable number of months, I would accept those answers as well. Part C asks us to identify the y-intercept. From our equation, we found that A was equal to 17.735. This is our y-intercept. So the y-intercept is 0, 17.735. And this tells us the initial value or the initial number of new COVID cases in January, because January is t equals 0. So this says in January, there were about 17.735 new COVID cases. And this is in Ghana. In Ghana. Okay, part D, what is the growth rate as a percentage for this function? So we are given from the equation, the base B. B was equal to 3.111. So then The relationship between the base and the growth rate is B equals 1 plus R. So 3.111 equals 1 plus R. That means R is 2.111. And if we convert that to a percentage, that's 211.1%. So each month, the COVID cases are increasing, or the number of new COVID cases were increasing by 211.1%. All right, on to part E. Using the model, what should be the expected number of new cases in October? So first we need to figure out what T is. October is the 10th month, but wait, we said January is 0. So then October will represent 9 if January is month 0. And then using our formula, N of 9 is 17.735 times 3.111 to the 9th power. Let's calculate this. That's a lot of cases. It would be 484,096 if we round to the nearest whole number. 96 new cases. So we started off with, according to this model, in January, 17, almost 18 cases. So we'd have, let's round up, 18 cases. And then by October, it's 484,000 cases. All right, part F. It says, write an equation to find the number of months after January in which the number of COVID cases reaches 60,000. Okay, so we're going to take that function, 17.3735 times 3.111 to the T power. And we want to know when this is equal to 60, or to the N power, sorry. No, it's T. When this is equal to 60,000. Again, we have an equation where we're trying to solve for the input and we know the output. Anytime we have a problem like this, for now, we're going to be solving graphically. We'll learn how to solve algebraically in a couple of classes. But we can solve this graphically by letting y1 equal 17.735 times 3.111 to the T power. Y2 equal 60,000. And then find the intersection. And we're asked to graph and round up to the nearest whole number. All right, let's do this. 17.735 times 3.111 to the X power. All right, I'm gonna have to change the window so that we can see y equals 60,000. So we're gonna let the y-axis go at least up to, say, 100,000. And then x is going, x is big enough. You can see the intersection point here is at 7.16. But it's saying to round up to the nearest integer. So that will round up to 8. Yeah, all right, so what does this number mean? How do we write out our solution to this? Let's interpret it. So 7.16. First, our graph looks something like this. Boom. That's not a straight line. Boom. That's y2. This one was y1. Our intersection point here was at 7.16, comma 60,000. And then what does that mean? Again, we're specifically told to round up to the nearest whole number. So we're going to round this up and show our work. This is saying that it took 7 months after January in order for the number of cases to reach 60,000. So what month would that be? January is 0. And then February, March, April, May, June, July. August would be 7. but it's after that. So we're rounding up, we'll round up to 8, okay? So this means after 8, or let's not say that, 8 months after January, which would be in September, the number of COVID cases, of new COVID cases, reached 60,000. So because this is a little bit bigger than 7, at 7 would have represented August. At 7 wouldn't be quite enough, so we have to go to the next month, which is 8 months later, so in September. All right, next part. What is the doubling time of the number of cases? Solve graphically and convert the units to days. All right, doubling time. That means how long does it take for any number of cases to get to double that amount? We can use our initial value to help us figure this out. So we have 17.735 times 3.111 to the t power. Doubling the initial value, 17.735, would give us 35.47. So we want to know, how long did it take to go from about 18 cases to about 36 cases? Or how did to go from 17.735 cases to 35.47 cases? How long does it take to double that? If we solve this, that gives us our doubling time. We'll do it the same way we did the last one. So our graphs, our pictures would look similar. We'll have an increasing exponential graph. Then we'll have the horizontal line. And then we want to find this intersection. All right, let's do that. 35.47. So y equals 35.47. Look how far down it is. You can barely see it. Let me make my window a little bit better so you can see. Let y go from 0 to 50. It's good enough. And then we see that intersection is happening at 0.611. 0.611. So that means that it's taking less than, less than a month in order for this to happen. Let's calculate exactly how many days it is though. So 0.611 is our point. That's right there here. So we have t is equal to 0.611 months. To convert from months to days, we have to multiply by, there are about approximately 30 days in a month. So 30 days over 1 month. If we multiply this, the months cancel. And we find our number of days. So that's 0.611 times 30. That's approximately 18.33 days. So what does this mean? Every 18.33 days, the number of new COVID cases doubles. So if it started off at 17, or about 18, I'll say, and after 18.33 days, it's doubling to about 36. And then after another 18 days, it's going to double again to 72. And after another 18 days, it's going to double again to 144. Every 18 days, the number of cases doubles. All right. So that's the last example that I wanted to do from section 3.4. Big things we need to be able to take from here. Regression's back. We do regression in every single unit, just with different types of regressions. So the last unit we were talking about linear functions, we did linear regression. Now we're talking about exponential functions, so we'll do exponential regressions. You need to know how to do all of those calculated steps to find your regression model, and then also know how to use it and interpret your answers. Dun, 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 dun. Section 3.5, compound interest and continuous compounding interest. The first couple of problems in this section have us break down step by step how compound interest works, and then it kind of helps us develop our formula that we're going to use for compound interest. We are going to do just a couple of these, get an idea of what compound interest is and how it works, and then we're going to jump to our formula and talk about how to use that to solve these problems. All right, so our first guided example, or actually, let's read this little spiel at the top. Interest can be thought of as money paid for the use of money. For example, when you borrow money, you pay back, like let's say you get a student loan or a car loan or any kind of loan. When you borrow the money, you usually have to pay back the amount that you borrowed, and you also have to pay interest on top of that. Interest is the fee that the bank charges you to borrow that money. Interest can also be a good thing when you invest money into a bank. That means you're letting the bank hold your money. Then they pay you interest for letting them hold your money. Okay, so depending on whether or not you're borrowing or investing, interest is either paid to you or paid by you for borrowing. So for the loan or for the investment. Okay, there are different types of ways that interest can be computed, or different types of interest, I should say. There's simple interest, there's compound interest, there's continuous compounding interest. Simple interest is interest that's only paid on the amount that you borrow. So if I borrow $100 and I'm paying 10% simple interest, that means each year I have to pay $10 for borrowing that $100, for however long I'm borrowing the money. Okay. Compound interest works a little bit differently because not only do you accrue interest on the principal, the amount that you borrowed at first, there's also interest on the interest that accrues. So it's interest on top of interest. In problem number 1, we're going to break down exactly how that works and how that changes how much money we would owe versus simple interest. Okay, so in problem number 1, we're going to compare 3 different situations. We're really only going to do 2 of them, but 2's enough. Okay. It says you inherit $5,000 and invested at 8% interest, and you have 3 plans to choose from. So when you invest your money, interest is a great thing. As long as you have the money sitting in your investment account, it earns interest, which is free money, right? The way that you earn your interest, or basically when your interest is paid, can vary though. The alpha plan that we have here says that our interest is compounded annually. What does that mean? That means that the interest is added to your account every year. So compounded annually means yearly, means at the end of every year or once a year, you get interest added to the account. Okay, so that's the alpha plan. The beta plan says we want to compound our interest quarterly. That means that at the end of every quarter, what's a quarter? A quarter of a year, which is 3 months. So at the end of every 3 months, the interest is going to be added to your account. Okay, but we have 8% interest for the whole year. Instead of getting 8% at the end of the year, you get 2% 4 times throughout the year. It still adds up to 8%, right? We'll see. All right, and then the delta plan says we're going to compound monthly. So instead of waiting every quarter or waiting to the end of the year, at the end of every month, or at some point during every month, your interest gets added to your account. All right, we're going to look at each of these and see how much we would have at the end of the year in each case. It might feel like you should have the same amount, but it turns out you're actually not going to have the same amount. First part, for the first year, we're going to start off with $5,000. And then we're going to add to that 8% of 5,000 because it says we're earning 8% interest at the end of the year, compounded annually. 8% of 5,000 is 0.08 times 5,000. That's 400. All right, so we'll have $5,000 plus $400, which is $5,400. Life's great. So at the end of the year, you have the $500 that you invested plus $400 more that you earned in interest just for letting your money sit there. All right. Another way that we could have calculated this is to multiply 5,000 by the growth factor. If we're increasing by 8%, the growth rate is 8%. The growth factor would be 1 plus 8%, which is 1.08. And if we multiply 5,000 times 1.08, we get the same thing, 5,400. All right, so after 1 year, we end up with $5,400. Now, in the second option, we said that we are compounding quarterly, which is 4 times a year. That's at the end of every quarter. And instead of just getting the 8% at the end, we're going to get 2% over time, or every quarter, I should say. So 2% after the first quarter, 2% after the second quarter, 2% after the third quarter, and 2% after the fourth quarter. All right, so we start off with our $5,000. And at the end of 3 months, we're going to increase by 2%. So remember, increasing by 2% means we want to multiply by 1.02. Okay. 5,000 times 1.02 would give us 5,100. Let me double check myself. I'm pretty sure. Yeah, that's right. $5,100. So at the end of 3 months, we'll have $5,100 in our account. Okay, so that sits there, and then 3 more months go by. So we're at the end of the next quarter. At the end of the next quarter, how much money do we have in the account? We don't just have $5,000, we have $5,100. So now we're going to multiply the $5,100 times 1.2%. So we're going to get 2% of the $5,000 that we started with, and 2% of the $100 in interest that we earned. It's compounding. You get interest on top of the interest. This would be $5,202. All right. So someone is asking, how do we get the 1.02? Does anybody understand where the 1.02 comes from? Or where the 2% comes from? All right. Well, we had 8% interest, but since we're compounding quarterly, we have to break that up over each quarter. 8 divided by 4 is 2. Okay. But 2% is a growth rate. 1.02 is the growth factor associated with that. So just taking our growth rate and finding the growth factor. Okay. And the growth factor is the same for all of these. So we'll keep multiplying by 1.02. We'll use the same pattern. Wait, where are we now? So we're at 6 months now. After 6 months, we have $5,202 in the account. We'll do this again for the third quarter. Now we're starting with $5,202. We want to multiply that by 1.02. Because at the end of the third quarter, we're going to earn 2% interest again. All right. Multiplying by 1.02. This gives us $5,306.04. And then finally, at the end of the year, we're going to multiply by 1.02 once again. That gives us our 2% increase. And let's see, $5,306.04 times 1.02. This gives us $5,412.16. All right, so let's look at the differences in these two. In both cases, we started off with $5,000. In both cases, we earned 8% interest. And we're doing this for 1 year. What's different is how often we compounded or how often we added interest to the account. The compounding frequency definitely plays a part in how much money you end up getting at the end, because notice if we compounded 4 times a year, we ended up with $12.16 more than when we compound only once a year. In general, adding your interest earlier, so compounding more frequently, is better because you start earning interest on the interest a little bit earlier. So all things equal, if you compound more often, you get a little bit more money if you compound more, okay? So we're not gonna do the Delta plan because it would take a lot of steps to do that, and I wanna get into the formula and actually doing some practice problems with this. But with the Delta formula, you would take 8% and divide it by 12, which would give us 2/3% per month. So each month, you get 2/3% in interest, and add that up, keep on going all the way into the end of the year to figure out how much you have. Okay, now, what I want us to take from this is a few things. One, a little bit of terminology. The original amount of money that we're investing, in this case, it's the $5,000. We call this the principal. The original amount of money that you're investing. The rate at which you're earning interest or accruing interest, it's called the interest rate. Just call this the rate, R-A-T. And then things like compounded annually, compounded monthly, compounded quarterly, these are called compounding frequencies. So how often is your interest compounded per month? And then we also need to know the time. This time we compounded this interest for 1 year. If you know all of those things, how much you're investing, the interest rate, how long you're investing, and how your interest is compounded, we have a compound interest formula that will show us exactly how much money we have at the end of the investment period. Okay, that's given to us at the bottom of the next page. Write this down, it's important, we're gonna use it a lot. The compound interest formula, okay? A of t equals P times 1 plus R over N to the NT. Lots of letters. We need to know what they all mean. So A of t is how much money do we have at the end of the investment after T years of investing at a certain interest rate, okay? Usually that's what we're trying to find. P is the original amount that we invest. This can also be applied to borrowing, so it could also be the original amount we borrow. R is the interest rate, has to be written as a decimal. Okay. N is the number of compounding periods per year. So this is important. If you're compounding annually, that's once a year. We just looked at a problem where we were compounding quarterly. Quarterly will be 4 times a year. If you're compounding monthly, monthly is 12 times a year. And our next example will actually talk a little bit about these different compounding frequency. And then the last thing is the time, and the time should be given in terms of years. If you know those things, you can use this formula to figure out how much money you have at the end of your investment. So we're going to do the same problem that we just did a second ago, step by step, with the compounding quarterly. We had $5,000 invested at 8%, compounded quarterly for 1 year. That's the example that we just did. And it came out to $5,412.16. We're going to redo that problem, but instead of doing it step by step, we're just going to use this formula. So with the information that we're given here, first, our A is what we're trying to find. P is equal to $5,000. R is equal to 8%, but we need that as a decimal, so that would be 0.08. N is the compounding frequency. Compounding quarterly means 4 times a year. So N is equal to 4. And T is the number of years. This one is just 1 year. So N is equal to 1. Putting this information together and using the formula, we would have A is equal to 5,000 times 1 plus 0.08 over 4 to the 4 times 1 power. Right, this should look a little familiar when we simplify it. We simplify this a bit, we get 5,000 times 1.02 to the 4th power. So that 1.02 pops up again. Again, that's just the growth factor, increasing by 2%. To do that, we need to multiply by a growth factor of 1.02. Right. If you put this into your calculator, 5,000 times 1.02 to the 4th power, you'll get the exact same answer we got when we did it step by step above, $5,412.16. The end. All right, so going forward, we're going to use this formula. We're going to want to take the information that's given to us in the problem, identify the principal, the interest rate, the compounding frequency N, and the time T. Put all of this into our formula and then use our calculator to simplify. On to example 2. Now, example 2 is the one where I told you guys we're going to look at the different values that we can have for N. These are the compounding frequencies that you'll be given regularly. If you see these in the problem, these are the N values that you should associate with them. Annually means N equals 1. That's it. Next, we have quarterly. Quarterly means N is equal to 4 times a year. Next is monthly. Monthly would be N equals 12 months in a year. Okay. Next, what else we have? Weekly. Weekly is, there are 52 weeks in a year, so 52 times. And then the last one that we're given here is daily. Daily would be 365 times. We don't count leap years, we just use 365. Another one that's not included in this table, but that sometimes pops up, is semi-annually, so I'll add that. Semi-annually is twice a year. So for our compound interest problems, you'll always be given a compounding frequency. These keywords tell us what to use for our values of N. For problem 3, it says John invests $2,150 in an annual interest at an annual interest rate of 2 1/4% compounded quarterly for 3 years. Use the compound interest formula to write the function A of t, then determine how much he should have in his account. Okay, so we're trying to figure out what A of t is. I'll write it in general. A of t is P times 1 plus R over N to the NT. In this case, look for these keywords that tell us our P, R, T, and N. First, he invested $2,150. That number represents the principal. Next, he invested this at an interest rate of 2 1/4%. This is the interest rate R, okay? You have to be a little bit careful here. Actually, I'm gonna write it over here. R is 2 1/4%. That's 2.25%. And we wanna write that as a decimal when we use the formula. So that would be 0.025 for R. The next thing, our compounding frequency. For compounding quarterly, that means N is equal to 4. And last part, we're doing so for 3 years, so T is equal to 3. All right, let's plug all of this stuff in. So we have A is equal to 2,150 times 1 plus 0.0, I missed the number up here, excuse me, it's 0.0225. 0.225 over what's in 4 to the 4 times 3 power. And then we want to put this into our calculator to help us simplify. For typing it into your calculators, you want to practice this too. It would just be 2,150, open parentheses, 1 plus 0.0225 divided by 4, close the parentheses, and then use the caret. And some of you will need to put your exponent in parentheses, 4 times 3. If you type it in this way, you should get your correct answer. All right, let's all take a moment to type this in. Okay. I got, is that right? Hold on, I missed something. Bad, Miss Ross. I forgot to divide by 4 in the parentheses. 2,150, 1 plus 0.0225 over 4 to the 12th power. Okay. So I got as an answer here, $2,299.70. So initially he had $2,150 in the account. And then after 3 years, the account grows to $2,299.70. That means he earned an extra, what's that, $149.70 in interest. Free money. Problem number 4. All right, so for the first one, James invested $350 at an annual interest rate of 2.5% compounded weekly for 5 years. Here, the 350 represents P. The interest rate is the 2.5%, so that's R. Just don't forget, you have to write it as a decimal in this formula, so that would be 0.025. We're compounding weekly, so N equals 52. And then T is 5. All right, so this gives us A of T equals, you can just write it as A equals 350 times 1 plus 0.025 over 52 to the 52 times 5 power. All right. Then from here, you put this into your calculator. I put it into my calculator a second ago, and we get $396.59. I don't think I've mentioned this yet, so let me mention it now about rounding. For these types of compound interest problems, we're talking about money. So when it comes to rounding, we should round to the nearest cent. So that's 2 decimal places unless otherwise specified. Sometimes a problem will say round to the nearest dollar, but if it doesn't say, round to the nearest cent. All right, on to the next one. Ashley invested $250 at 5% compounded monthly for 10 years. This would be A is, not 250, 2,500 times 1 plus 0.05 over monthly, so 12. Uh-oh, I don't think I did this one right. Oh, no, I did. Raised to the 12 times 10 power. When we put this into our calculators, we get $4,117.52. All right, and for our last investment, Brian invested $4,000 at an annual interest rate of 3.25%, compounded quarterly for 8 years. This would be A is equal to 4,000 times 1 plus 3.25% is 0.0325. We're compounding quarterly, so over 4, and then it's to the 4 times 8 power. Right, that would be $5,182.27. Let's go on. We'll do number 5. Number 5 says Mike invested $10,000 for his retirement fund at an interest rate of 11% compounded monthly. How much will Mike have 35 years after the initial investment? So the P in this case is the $10,000 that we're investing. The interest rate is the 11%, so R is 0.11. We're compounding monthly, so N is equal to 12. And we're told that we're doing this for 35 years. That's a lot. So T is equal to 35. Then A would be equal to 10,000 times 1 plus 0.11 over 12 to the 12 times 35 power. So this will tell us how much Mike has in his investment account. Notice he only puts his $10,000 in, and then he just lets it sit there for 35 years. Okay. How much does he end up with? He would end up with $461,760.50 if he leaves this money in there for 35 years. The second part is asking, well, what happens if he leaves it in for 40 years instead of the 35 years? So we'll almost have the same thing, except T will be 40 in this case. That's 10,000 times 1 plus 0.11 over 12 to the 12 times 40th power. Okay. If he just has the money or leaves the money in the investment account for just 5 more years, he ends up with $798,344.99. The idea here with investing is invest early so that you can keep your money in the account as long as possible, because in those last few years, your investment account should grow a lot. Now, of course, in real life, your investments depend on what companies you buy stock in and all kind of other stuff. But just in general, invest longer, you'll end up with a lot more money in the long run. Number 6 is another interesting one. It says, suppose that $1,000 is invested at 8% compounded quarterly. How much is in the account at the end of 3 years? And then we're going to compare that to having $1,000 invested at 8% compounded daily. We saw earlier in the first problem that we did, when we looked at compounded annually versus quarterly, that the more you compound your interest, the better. You end up with a little bit more money. But this is just going to show that one more time. Okay. So we would have A is equal to 1,000 times 1 plus 0.08 over 4 to the 4 times 3 power. Okay, that's if we're compounding quarterly. For compounding daily, you would have A is equal to 1,000 times 1 plus 0.08 over 365 to the 365 times 3 power. The second one will have $1,271.22. And then for the first one, $1,268.24. So we can see if everything else is equal and all we're changing is our compounding frequency, the more you compound, so the more often you compound your interest, the more money you get. But notice it's just a little bit of a difference, but I would take it. Every penny counts, but you get a little bit more. This is about what, $3 more if you compound daily instead of quarterly. Right? That brings us to another very important question. Is there a upper bound to this? So we're saying, oh, the more often you compound, the more money you end up with. So somebody might be thinking, well, I want to compound all the time. Instead of daily, maybe I want to do it every hour or every minute or every second or every millisecond. Or I want to compound interest all the time. It's called compounding continuously, which we'll talk about in a second. In this table, this one's done for us, which is nice. We can see what the difference is in a similar situation. This goes back to example 5. Suppose we experiment with the value of n from example 5. We're looking at the guy that had $10,000 invested at 11%. He's making this investment for 6 years. And we're looking at compounded monthly, daily, hourly, every minute, minutely, and every second. Okay. If he compounds monthly, he has $19,289.84. That's the amount that's right here. Great. If all we change is the compounding frequency, you go from monthly to daily, the amount goes from $19,289.84 to $19,346. So let's see what that difference is. The difference is $56.16. So if you go from compounding monthly to daily, that increased your output by $56.16. But look at the difference between daily and hourly. You go from compounding daily to compounding every hour. You go from 19,346 to 19,347.84. So that's only an increase of $1.84. And then if you go from hourly to every minute, it does increase, but only the cents are changing. We go from 84 cents to 92 cents. Okay, I'll take it. So that's an increase of 8 cents. And then again, and this is probably just because of rounding, we have an increase of about 9 cents here. That's probably a rounding error. As we can see, yes, we can compound more and more frequently, but the change in our outputs aren't increasing as much. There seems to be a bound on it, and there actually is a bound. It's bounded by the number E. So what is the correlation between how often compounding occurs and the investment amount? The more often you compound, the more money you end up with, but it goes up by smaller and smaller amounts over time, okay? Then someone had the great idea to say, oh, well, let's compound continuously. I always want to compound my interest. And that brings us to our second compound interest formula, which is the continuous compounding interest formula. So for compound interest, N represents periodic compounding. That means you're compounding your interest at specific time increments, okay? If periodic compounding is every day, every hour, every minute, or every second, we then, and it keeps going, like all the time, we consider this to be continuous compounding. And for continuous compounding, we get the formula A equals P times E to the RT. This is still an exponential function. P represents the principal still, A is still the amount at the end, T is still the time, R is still the rate, the interest rate. Okay, what's different here? We have this number E now that we're going to be using for our base, and there is no N when we're compounding continuously. Okay, so you only use this formula when you see specifically that you're compounding continuously. If you're given compounded daily, weekly, monthly, hourly, you use the other formula. Only for compounding continuously, you use this one. All right, then to finish out this section, I think we have like 2 more examples to do. We're going to look at a couple of examples where we compare compounding continuously to compounding at a certain periodic compounding period. And then I'll just make sure everybody knows how to find the E button on their calculator. So I'll show you an example with that. Problem 8 is a worked example for us, so we're going to skip that. We're going to do problems 9 and 11. Those are the last 2 non-worked examples. So problem 9, Rob has $20,000 to invest for 10 years at an interest rate of 10.5%. What will be the results of the investment if Rob chooses to compound daily? What will be the results of the investment if Rob chooses to compound continuously? So first, if he's compounding daily, we use the formula A equals P times 1 plus R over N to the NT. If he's compounding continuously, we use the formula A equals P e to the RT. All right, for both of these, P is equal to 20,000. R is equal to 10.5% as a decimal, that's 0.105. And then T is equal to 10. All right, and when we're compounding daily, N is equal to 365. So we would get 20,000 times 1 plus 0.105 over 365 to the 365 times 10 power. And then we have to type this into our calculator. All right, that will leave us with $57,144.39. So with this situation, if we compound daily, we get $57,144.39. All right, if we compound continuously, we would have 20,000 times e to the 0.105 power times 10. When you type this into your calculator, it should be 20,000. And then there is a button that says e to the x. You have to press second and then LN. That's the button next to the 4 on your calculators. So you'll press E, and then the caret symbol, 20,000 E raised to the parentheses 0.105 times 10 power. Where's my E button? All right, 20,000 E to the 0.105 times 10. All right, this one gives us $57,153.02. So we can see here that when we compound continuously, we end up with a little bit more money than when we compound daily. So which of these investments would you choose? The one that gives us the more money, most money. So compounding continuously. All right, you have a problem on your lab that's very similar to this, where you're comparing compounding, I think it's compounding quarterly to compounding continuously on that one. All right, the last thing, the kind of growth model that we see when we do continuous compounding interest is called continuous growth. We can also have continuous decay. Those are models of the form y equals a times e to the RT, or sometimes it's KT. To determine whether or not you have a growth or decay, it depends on whether the exponent on the e is positive or negative. If you have e to the x, so a positive exponent, that would be an exponential growth. And it'll follow our exponential growth models. If you have e to the negative x, that's a decreasing or a decaying exponential function. So your exponent's negative, well, your base is e. If the exponent is negative, that's a decay or a decreasing function. If the exponent is positive, that's a growth or an increasing function. We're going to use this in our last problem to identify when we have exponential growths and decays, looking at our two different models. So we have, let's see, y equals a times b to the t, and y equals a times e to the, it's either kt or rt, depends on what book you're using. RT, okay? For something of the form a times b to the t, we have a growth when b is bigger than 1. We have a decay when b is between 0 and 1. We've seen those problems before. For something of the form y equals a times e to the RT, we have a growth when the R value is positive, and we have a decay when the R value is negative. Right? Let's look, and in all of these, a represents the initial value. So for the first one, 23 times 1.05 to the x power, the initial value a is 23. The base is 1.05, which is bigger than 1, so this would be a growth. And then we're asked for the growth rate. For a growth rate problem, B is equal to 1 plus R. So 1.05 equals 1 plus R. That means R is 0.05 or 5%. So we're starting out with 23, and then our outputs are increasing by 5%. All right. For the next one, 2300 times 0.85 to the x. A is 2300. Our base here is 0.85. That's less than 1. So this would be a decay. And then the relationship is B equals 1 minus R for decay factor and decay rate. So 0.85 equals 1 minus R. This means R would be equal to 0.15 or 15%. But we're decaying by 15% in this case. All right, for the rest of these, I'll make it a little bigger. We want to look at the exponent on the E to determine if we have a growth or decay. Positive exponent growth, negative exponent decay. The A value is still the number being multiplied out front. So for y equals 540 e to the negative 0.45x, A is 540. This is a decay because our exponent is negative. And the coefficient in the exponent tells us what our decay or growth rate is. So our decay rate is negative 0.45. This is a decay of 45%. All right, for the next one, f of x is 98 e to the 0.15x. A is 98. Here our exponent is positive, so this one is a growth. And that positive exponent of 0.15 tells us that we're growing by 15%. And last one, g of x is 45 e to the 0.36x. A is 45. Again, our exponent is positive, so this one is a growth. And 0.36 tells us we have a 36% growth rate.